you know, because
I think that's a fair enough request. Why not?
okay. And the second thing is that the recording did not happen is because I guess you tend to pause it during the break. So the other request is if you don't pause it, then at least the recording will go on and we can always, you know, fast forward and watch it. So that way nobody nobody will have to start the recording again.
Okay, fine, not a problem.
Yeah, those are the two requests I have. So it will be very helpful if you can just do a summary of what you discussed. I think it was a last hour that you talked about.
Yes,
I think classification metrics. Yeah, because I think that's a very important topic in machine learning, and will be good to sort of.
Let me pull that out.
Great. Thank you so much. I really appreciate it.
Yeah. Anything else from anyone? Anything else from anyone else? Yeah, Shrikant, I'll unmute you. Just a moment. Okay, yeah, I've given the permission to talk.
So thank you, sir. So actually what I observed in the last session and also in the session before that was this gap in the recording happened because the moment the session started, got a message, you know, saying which we normally get after the end of the session of the recording of the session itself. But that was basically blank. So that's why, you know, this problem can happen again. So
see, that is something which is completely technical and probably not in my hand, right? Probably
so it's not actually technical, so because this has not happened previously, and this I'm observing is happening particularly in this term. I don't know if it's a issue with coordination with the moderator or not, but I noticed that this happened in 2 sessions in this particular machine learning itself. That's why I'm pointing out. Otherwise, I wouldn't.
Sure, yeah, something might have happened. That's why it's, it's coming to your observation. So maybe what we can do is, if you guys are having some some kind of a student coordinator within yourself, maybe that person, he or she, can probably check from time to time regarding.
Actually, what happens is we have one student buddy assigned for the entire term, but for every session, there's a different coordinator who, you know, starts the recording and then sends it over in the group when the class is finished. So it's recording with, you know, it's every time you have to coordinate with different people. That's why I'm saying that's all.
See, that is again not something which is in my purview. Otherwise, I definitely would have stepped in. Yeah, what I'll do is, so I come from the NM side, so I'll probably have a word with NM and try to see what.
Okay, fine, sir.
Fine.
Thank you.
Okay. So, as requested, quickly, I'll go through the metrics part, right, before we get started. So let me quickly project my screen. So yeah, for the machine learning. Okay. By the way, voice, video, everything is okay. No issues with that. I hope so. Right? Okay. So machine learning metric, if we look into it in the first place, the first thing that we do for machine learning is that we create a model and we train that particular model, right? And then we do some kind of a validation also on the whatever the training has happened. Now, in this whole aspect, in this whole part, the problem is that the data part, right? One is the data is a problem itself, right? Now that data problem, how we are going to mitigate, I'm going to talk about it later. Just a moment. Yeah. So that mitigation part we are going to discuss later in this particular term only. I think probably in the second or the third class we are going to discuss. But otherwise, how we are going to ensure that a model is good, right? So that is where the machine learning metric comes in, and we have a specific metric for classification as well as regression. For the classification metric, right? So typically classification, it relates to some kind of a classes, right? And the metric should be able to give us an indication that whether we are doing a good job in identifying the classes or not, right? For the case of a regression, where the output is continuous, some kind of a numbers, right? So we are going to find out that whether the amount of deviation from the actual value, how much is that? That's the basis for the regression models, right? So, and then we also have some kind of output which is probability that comes from something called as a logistic regression, or also from your need based which we have done in the class, right? So these are the metrics for regression model: MAE, mean absolute error; MSE, mean squared error; RMSE, root mean squared error; RMSLE, root mean squared logarithmic error; and the R squared, the adjusted R squared. So quickly, the first one, mean absolute error. Right? Error part, as I've said, that whatever your model has predicted and whatever is the actual, that particular deviation is the error. Right? So absolute error is that you take the absolute value of that particular deviation, sum it up, divide by total number of observations, that will give you the mean absolute error. Right? So all the individuals, they will be having the equal weightages. And again, I think the outlier part we have discussed in quite details, that in cases where maybe one or two outliers are there, so there the deviation will become large, the error will become large. But again, if you are having a large number of observations, what will happen is that this large deviation or this problem, that will get less amplified, and it will get averaged out over the entire total, right? So this is the MAE, or the mean absolute error. Next comes the MSE, or the mean squared error. As I said, that here you take the error part and you square up the error, right? So this is the most preferred metric for regression, right? Which is there. And what happens is, since you are squaring the differences, whatever differences we are talking about, this error part, since you're squaring that error part, so what happens is that the error gets amplified, right? The part where the error is very small or negligible, right? The mean squared error is also very small. In the case the error is large, the mean square error that amplifies and makes the error even larger, right? So that was the mean squared error. And then, as I said, that for the mean squared error, what happens is, since you are squaring things up, if the difference is large, when it squares it up, it becomes much more amplified, right? That is where the RMSE, root mean squared error, comes in, right? So here, what we do is that the mean squared error, we just take the square root of it to give the root mean squared error. So in essence, it still has the flavor or the entire idea of the mean squared error. But again, in terms of the dimension or the size of the error, that size, in terms of the size, that gets crippled, but not the implication, or not the whole idea against which the squaring was done, the error part was done, right? And then this RMSLE, I discussed this. So RMSLE, what happens in the case of RMSLE is that in the case where the errors are large and wide apart, right? So say, for example, your predicted value is 10 and your actual value is, let's say, 1000. The difference becomes 990, right? 990 squared becomes very high, right? The problem which we saw in the this RMSE part of the NSE part. So there, what we do is that to counter this very large errors, because the problem with a large error value is that it will be very difficult for the model to optimize when there are errors which are of different dimension. One error is, let's say, 5. One error is, let's say, 12. One error is, let's say, 1000, 5000, 20,000. It becomes very difficult for the model to optimize that. Right? So here, what we do is that we take the logarithm value of the actual value and the expected value. So the difference of the actual and expected of the logarithm value, we square it up, right? And find the average, and then the root mean of it, that gives a root mean squared error, or RMSE, right? RMSE. So, right? So, yeah. And the last one was the R squared error, also known as the coefficient of determination used for regression problems. Right. It generally lies between 0 and 1. We have discussed this, and this is the formula for this R squared error. 1 minus mean squared error of the model divided by mean squared error of the case time. As we understand that if it's a good model that we have created, the mean squared error or the error part will be small. So 1 minus a small value will be very close to 1, which means this R square value will be almost as close to 1 as possible, right? A value close to 1 is good in this particular case. The baseline part is where we are finding out the deviation just from the average of all the values, right? In the worst case, the model works as good or sometimes as bad as the baseline part, and in that particular case, the R square becomes 0, right? See, let's say you get the R square value as, let's say, 0.80. Now, what does it mean? What does it mean? It means that if you have built this particular model, right, whatever model you have built, obviously to build this particular model, you have considered some variables in the process, right? So whatever variables you have taken, that variable, all those variables combined together is able to account for, let's say, 80% of the variability which is there in this particular model, right? That is R square value of 1, right? Let's say you get R square value of 0.3, right? So R square value of 0.3 means that whatever model you have created, right, the variability in the model, 30% of it could only be explained by the variables that you have considered for this particular model, right? Okay. So next quickly come to the case of this classification metric, right? In the case of classification metric, like unlike regression, those are some specific classes which will come, right? So with regard to that, what can happen is that you have created a model, right? So whatever the actual value is there, that is what the model is predicting. So excellent model, right? Or otherwise, the model is predicting something and your actual value is different. That is where the problem is there. Right? So but this particular part, right, there is this concept of true positive, true negative. Now, what is positive and negative, right? So typically, positive is something, a particular value that you are interested in, right? Positive value. Right? So let's say, for example, in this pandemic time, I give that example. Many of us, we had to undergo through that blood test, right, for COVID, right? So here my target was to identify COVID, right? So a positive result coming out of it means that I've been affected by COVID. So many people, they get confused that, sir, why I mean something bad is positive. It's not that something bad is positive, but if I'm saying something is positive, right? So whatever is my variable of interest, whatever is that I'm trying to measure, so that has that particular thing has actually occurred, right? So let's say that this seismographers, right, or geologists, they measures the propensity of chances of all these earthquakes, tsunami, and let's say their machine shows that there is a high chance or high probability that somewhere earthquake will happen, right? So what is happening is that the propensity of that particular thing happening, that is high, right? So that machine will give you positive for the occurrence of the earthquake. So again, earthquake is not positive thing, right? But the measurement of that thing came out as positive. Right? So I hope you got the idea, right? Again, so similarly, I mean, we have heard of HIV positive kind of thing, right? How it can be positive. Right? So positive is with regard to the measurement. So here we have two things. One is something called as true positive. The other is something called as true negative, right? So true positive is what that you had predicted. So this particular values, positive, negative, are what you had predicted. So true positive is that you had predicted to be positive, right? And actually it was found to be true, which means that whatever was the prediction from the model and whatever was the actual thing, they matched. So that's a true positive case, right? Come to the case of true negative. The model said negative, right? That was predicted by the model, and that was actually true. Right? Model said negative, and actually also it was negative. So that is the case of true negative, right? Come to the case of false positive, right? So model is saying positive, right? Model is saying positive, but again that thing is false. Right? So from your symptoms, maybe see all these days, thanks to Google, all of us we are doctors, right? So you have some symptom, you check Google, you find a list of elements of problems, and you say that okay, seems that I'm positive for this particular disease. And then when you go to the doctor, doctor says no, that's not the case, right? So you have predicted positive, or your model had predicted positive, but that was wrong, untrue. So that's the false positive part. And then similarly, false negative. right? So the model had predicted negative, but actually it came out to be not negative. It was actually a case of positive. So many a case, if you remember that the tests they came out as negative, and we used to say for this COVID asymptomatic, right? Those kind of pieces, right? So you're predicting negative because there are no symptoms, but actually after doing the test, it came out as positive, right? So these were the asymptomatic cases, just for your own reference. So obviously you understand that false positive and false negative, they are not very good or healthy for my model. So what I should try to do is that the false positives, my model should be good enough or equipped enough to convert the false positives to negatives, and the false negatives, the model should be more trained so that the false negatives could be identified more as those of positives, right? Okay, and with that particular regard, uh, we have something called as this confusion matrix. What exactly is this confusion matrix? Right? Confusion matrix is actually geared to ensure that you don't get confused in this whole jargon of positive, negative, all this part. So two things which you have to keep in mind is what is that your model is doing, model is predicting, and what is uh, happening actually or in reality. Right? So here you see the model is saying positive, and the target or the actual value is also positive. So this particular part A is where the model will also say that it is A, and your actuality is also A, right? So that's the case of the true positive part. Look at the case of D. So in the case of D, the model is saying negative, right? And your target value, right? So model is saying negative, and your target or the actual value, that's also saying negative, right? So both of them, they are negative. So which means that model is doing as per expectation. So that part is fine. Come to the case of this B, right? So B, what has happened out here is that the actuality, this particular case is that of a negative case, but the model has said that it is positive. So this is the case of a false positive. So B is a false positive. Why? Because the model has predicted it positive, but actually it is not. It's actually negative. Come to the case of C. So C is false negative, right? Why? Because the model is predicting that it is negative, but actually it is not. It is actually positive. So it's a false negative, right? So positive predictive value or PPV is of all the values which were predicted as positive. So A plus B, right? Those are all the values which were predicted as positive. How much of it is actually positive? So of the A plus A plus B values which were positive, only A of A is A out of that is positive, right? So yeah, so that is the positive predictive value, A by A plus B. Similarly, negative predictive value, how much of it has been predicted as negative? C plus D has been predicted as negative. How much of it is actually negative? D. So D divided by C plus D, that's a negative predictive value, right? Okay. Accuracy part. Accuracy is take all the cases which you're trying to classify, right, as positive or negative, and of all the cases which are there, how many of you were correctly identified as positive, and how many of them were correctly identified as negative? So A were correctly identified as positive, D correctly identified as negative. So A plus D is the cases where your identification was correct, true. So A plus D divided by all the cases, A plus B plus C plus D. Right? So that's the accuracy part. Right? Now come to from the point of view of the actual values. This positive predictive value or the negative predictive value, that was from the point of view of the model. Let's come from the point of view of the actual values. So that brings us to something called as sensitivity. Right? So sensitivity is that of all the this thing positive values, right? How much of it was actually identified by the model? So A plus C was all the cases which were positive, A plus C. And of that, actually identified by the model was only that of A. Right? So if I show it here, so here this one was actually positive and identified by the model, and A plus C is all the cases which are 2D positive. Similarly, the specificity part, all the cases of negative B plus B, all the negative cases of which D are the cases which the model also had perfectly identified. So specificity is the E divided by B plus, right? So that was the confusion metrics. Again, terminologies you can just read. I've already explained. So yeah, this is the case of your actual reality, and this is the predicted. So here, if you see, reality is all these cases: actual positive, actual negative. So these are the cases of actual positive, right? And these are the cases of actual negative. So accuracy is 2 positive plus 2 negative divided by all the cases: 2 positive, false negative, false positive, 2 negative. That is the accuracy part, right? Now that also brings me to something called as type 1 error and type 2 error. So type 1 error is where your model has said it is positive, but that was false. So the false positive cases are called the type 1 error and type 2 error. Right? So here you had predicted this as negative. The model had predicted this as negative on the type 2 part, right? But again, that prediction was wrong. So that is the type 2, type 1 error and type 2 error, right? Precision or the positive predictive value. Precision or the positive predictive value, right? So what are the values that you had actually predicted as positive? So this is TP plus FP. Those were actually predicted as positive, and of which how much of it is positive is the TP part. So TP divided by TP plus FP is the precision or the positive predictive value, right? Similarly, the sensitivity, or also called as the recall value, is of the real positive cases, which is the TP plus this FN, right? Actual positive cases. How much of it is to be positive? Right? So TP divided by TP plus FN, that is the sensitivity, right? So these were the metric. I had done this small problem in the class, right? It is already there in your shared PPTs. So one last thing, two things I have to discuss, right? So this was something that we had spoken of, right? You were asked to build a model classifier for leukemia. Training data had only 1% patients with leukemia, while the 99% of the people, they were healthy. Right? If you measure the accuracy as the metric, will that be good or not? Now the answer for this is that, see, your 1% patient is having problems, issues. 99% they are healthy. Right? So let's say that your model is heavily biased towards identifying or towards saying that patients are healthy. Right? Because the data is so much skewed, what will happen is that even if you don't do much on this, right? So even if your model is doing very bad on those 1% patients, still more than 99% of the cases, the model will be correct, right? If you use the accuracy of the metric. So probably not the best metric out in this particular area, right? So in this particular case, rather than accuracy, if let's say leukemia is the positive class, had you used the sensitivity or the recall, or maybe the precision or the positive predictive value, right? That probably would have been much better metric out here, right? Because again, here your whole diagnosis should find out that whether patients are having leukemia or not, right? So yeah, and that brings me to something called as F1 score. Right? So F1 score, what happens is that on the part of your precision or the positive predictive value, it finds out that of all the cases which are rated as positive, how much is actually positive. And then the recall part is that of all of the actual positive cases, right, how much of the model has been able to identify. So both are important from their own perspective. One perspective is from the perspective of the real cases, and one perspective is from the point of view of the prediction part. Right? So both of these are important. So what we are doing is, again, people says that okay, this is important from the prediction point. Some people will say no, from the actual point, the recall part is important. So this particular metric, which is the F1 score, what it does is that it creates a harmonic mean of both the precision and the recall, right? So again, not the exact mean, right? So if you see, you'll see the problem with the mean, right? So your positive predictive value, this is your 2 positive divided by 2 positive plus false positive predictive value, and recall or sensitivity equal to 2 positive divided by 2 positive plus false negative, right? If you find out the simple average, what happens is that, see, the base is different for both the cases. So you can't actually find out the normal average, right? So that's why we are taking the inverse of it. So if you inverse this, this will become TP plus FP divided by TP. And if you inverse this one, it will become TP plus Fn divided by T. Now you see that the bases are the same, TP, DP in both the cases, right? 2 positive cases. Now you find out the average of the inverse, and then you inverse this value. So that will basically give you the harmonic mean or the one score, right? So a very important metric which we have, right? And the last thing which we had was probably the ROC curve, the receiver operating characteristic curve, right? What happens in the ROC curve is that on this particular part, we are measuring the sensitivity, right? So how much sensitivity is your model? So the higher the better, right? The higher the better on the part of the sensitivity, right? More value, better it is. And on the part of the x-axis, right? Right, we are finding not the specificity but 1 minus specificity, right? So specificity is the basically the rate of the true negatives, but here we are finding out the complement of the specificity. See, all these are probability values. We are finding out the inverse, so which means that lower it is, the better it should be. Specificity, higher it is, better it is. 1 minus specificity, lower it is, the better it is, right? So this particular curve, this receiver operating characteristic curve, so this particular part, once you plot that, the area under the curve also you measure. It is called the AUC, area under the curve. A high AUC means that your model has done a good job in identifying both the instances of the positive cases as well as the instances of the negative cases, a high value of the ROC curve, right? See the part where it goes through the middle, this particular part, it just goes through the middle. So this particular part, what happens is that as and when the sensitivity is increasing, right? Now you're increasing the sensitivity, right? The complement of the specificity, that also increases. So which means that if I'm trying to increase the identification rate of my 2 positive cases, my identification of the 2 negative cases, that goes down, right? And vice versa. Here, the identification of the 2 negative cases are probably almost this one, the chance of making the error on the 2 negative cases. So specificity will measure the 2 negative cases, and 1 minus specificity, right, will measure that how much error you're making. So the lower the error, the better it is. So at this particular point, what has happened is that you are having a low error value, which is good, which is fine for us. But again, on the 2 positive cases, that's also bad. So here, your 2 negative cases at this particular point, that identification part is very well, but the 2 positive cases identification part is bad. Now, as and when I'm increasing on this particular part, so my 2 negative, it goes down, comes down, as and when I'm increasing in this particular part. So 2 negative goes down, right? And then this 2 positive rate, it goes up. So somehow there is some problem in this particular part, right? So the ideal case is this particular curve which I've shown you, so which is very high on the 2 positive part, as well as pretty low on the 1 minus specificity part as well. So that was in a nutshell the metric we had discussed. So for people who had requested this, I hope it helped, right? Okay. So, yeah, any questions from this before we get started with our actual part? Any questions? Questions? No? Then let's move ahead to what we were supposed to cover today. So what I'll do is I'll just turn off the video. Okay, now let's focus on this part of, yeah. Okay, so here today's class, generally what I cover in the first class is one of the very important optional contents, which is that of the recommender system, as well as I give a overview of what we are going to cover and start off with the first topic. But here today, what I'm going to do is, since we had taken some time to cover the previous part, so the optional content, the recommender system part, which is not included in your evaluation or exams, this was more from the learning perspective. I'll just briefly touch upon that, and then probably I'll move ahead to the main parts. Right? Okay. So these were our machine learning vocabulary, all the things. So already of this, let me tell you, we have already covered what is machine learning, what is supervised learning, what is unsupervised learning, key nearest neighbor, naive Bayes, regression, logistic regression, model evaluation, right? Model metrics. These are some of the things which we would have already covered. The PCA part has not been covered. Yeah, that I think comes up in your machine learning 3, the PCA part. Okay. So this recommender system, just will give you a small overview for 10 minutes, and we'll move on. So there are these theories of this collaborative filtering, content-based filtering, knowledge-based, hybrid strategies. Now, what exactly are these, right? So examples of recommender system, you already know that whenever you are watching Netflix, you are giving these recommendations from for some other movies, shows, right? Whenever you are browsing something on Amazon, the other recommendation comes up, right? So what are those things exactly, and how does it happen, right? So again, this is, by the way, the book which was used for this particular content. So again, by the way, my the PhD was also in the area of this recommended systems. So when Netflix had launched that competition, $1 million for the best recommended system, right? So like many researchers in the world, I also had taken up part in it. Anyway, so these are probably some of the problems. Which digital camera should I buy? Best holiday for me and my family? Best investment for supporting the education of my children? Which movie should I when? Which websites will I find interesting? These are some of the popular topics, right? Popular questions which are being answered by recommended systems, right? Say, for example, which digital camera should you buy, right? So what you do is that you maybe go to the feature lists, reviews, and then you probably go ahead and purchase it, right? So this was maybe driven by the content of that particular camera, content of the features and everything, right? So that is probably what you are interested in. Feature list, reviews, right? That only drives that which camera should you buy, right? The other one, which is the best holiday for me and my family, right? Best holiday. One part is that you're probably someone who loves the cosmopolitan cities, or maybe the mountains or the seas. So that is when it is being driven by the content part, the feature part. Right? Okay, this is a place where the sea is there, right? This is a place where a lot of tourists will be there, good eating joints. So those were the feature part. So that brings it to the something called as a content-based recommender. But sometimes there is also something called as a collaborative recommender system. What is collaborative? It is more of a social process. So it's almost like, okay, my next door neighbor, Guptaji's wife, she is boasting of her trip to Europe, Eiffel Tower, and all these other places, this holiday in Switzerland. So because there are people in my social network who have experienced something, I would also like to experience the same thing. Right? That is the whole notion of collaborative filtering. Right? In the case of Netflix, right? I'm sure that many of you probably are subscribers of Netflix. So in the case of Netflix, what happens is that when you open Netflix, it will show you, right, the top 10 shows in India today, the top 10 trending movies in India today, right? I'm sure that you have seen that. So those parts are nothing but the collaborative filtering, right? So here, when you're talking of India, so once again, you are referring to a particular region or a particular social boundary which you have given, right, based on the country. And in this particular social region, which is basically this particular country, what people are viewing, right? So that is the process of collaborative filtering, right? So again, what happens for recommender system is that it's a technological proxy for social processes, right? So again, you guys have, like many of you, probably most of you, have basically lived in this era, digital era, right? Digital era, you have matured in this particular age. But during our time, right, what used to happen was that if I had to watch some movie, right, I had to go to this movie library, rent that video, and obviously it was cost money, right? Not like that we had something like a YouTube. So that's why we used to do was that social network was also not there. So we used to go about and ask people that, okay, this particular movie, what do you think? I mean, how good is the movie? Should I really take this up? Right. So today, what is happening is that whole social process. Right? Today, you have to buy something. You don't go out and seek your friends who have bought that particular part. Just go online and see the reviews, right? So our entire social process has been converted uh, to some kind of a technology, right? So recommender system exactly does that, right? So on the part of the content-based recommender system, right? The content-based recommender system, what it is doing is that it is basically becoming a social proxy, right? It's becoming a proxy for a real event where based on the contents, you are finding out that what exactly are the other things that you would like to have, right? So rather than you doing it on your own, a technology system is doing that, right? Also for the part of the social process, where we said that it's also a social process. What we do out there is that we see people in your vicinity, right? The basis your particular kind of tastes, preferences, your kind of profile, right? So for those people, what is that people are enjoying, and based on that, that has been recommended to you as well, right? So what happens is the whole point of finding people who are similar to you, or finding items which are similar to the item of your choice, that particular part has been automated thanks to technology, right? So yeah, this is a motivation, automation of the word of mouth thing, right? And again, a lot of customization is there. So customization is when you are bringing your own preferences as well. For example, the first case is when we were talking of this buying this digital camera, right? So digital camera you would like to buy, which is fine, which is good. But in the process of buying this particular digital camera, right? You probably like all the features, everything, but again, the price of the camera is very high. Obviously, you will not be then interested in buying that particular camera because it doesn't match your budget. So whenever you apply that particular kind of a constraint on the recommender system, so that is also something called as a knowledge based on some specific knowledges, right? Based on some specific parameters, you are fine tuning the recommender system, right? And also you have something called as a hybrid recommender system. So hybrid is a mix of knowledge-based, content-based recommender, collaborative systems, all that, right? See, I mean, Jeff Bezos, see, that's why, I mean, he was the richest person in the world for quite some time. So he had famously said that if I have 2 million customers on the web, then I should have 2 million stores on the web, right? how deep and how impactful this particular word that we have said, right? If I have 2 million customers on the web, I should be having 2 million stores on the web, right? Fabulous, isn't it? Right? Okay. So yeah, this is the power of personalization. What happens is that it turns browsers into buyers. I'm pretty sure that many a time you just going around and browsing on, let's say, Flipkart or Amazon. You didn't have any intention to buy also. Just because something was recommended to you, you saw something on deal, you probably purchased that, right? I'm pretty sure that many of you have done that. So that whole process of giving you those recommendations, giving you those deals, that also comes via a very smart automated process, right? So that is where even a non-buyer, you have converted a non-buyer into a buyer, right? Those kind of a thing happens, right? So cross sells, the other part, customers who have bought a particular product are suggested some kind of a related product. That also happens, right? And it also encourages loyalty, right? Why loyalty? See, I mean, if you find that here is one website which understands my preferences, my tastes far better compared to anything else. Let's say it's a trip website like a let's say a Make My Trip you're using or a Clear Trip you're using. When you're booking, it already knows that you're probably someone who likes non-smoking rooms in hotels. You probably would like to have, let's say, a veg dinner. So all those things it pre-fills for you, right? So some kind of a loyalty is there, right? So since it encourages loyalty, so those are also some of the reasons why recommender systems are highly being used. Right? So all these different businesses these days, you find that they have come up with this e-cash, like this wallets and everything. That's nothing but some form or the other of the loyalty card, right? Okay, so yeah, these were something which I was saying, right? The social part, population based, move like top 100 movies, top 10 best movies today, item to item, content based, right? So all these things are the different kinds of recommendation systems. So this slides they have been shared with you, right? I'll not go into further details, but again, you can read it. It's a fascinating field. It's a fascinating field, and again, this is something which probably will never go out of place, right? See, I'll come back to Netflix once again because again that's an amazing company, right? So Netflix is a much smaller company organization compared to the likes of Amazon or Google, right? Or let's say even your Microsoft, right? Now, all the services, right? Amazon has its Amazon Prime, Google has its YouTube, right? Microsoft also are basically powering many of the streaming services, right? So again, by the way, I mean, you see all this now, this Hotstar, this Z5, many of these are actually powered by Microsoft's own proprietary engine, which it has given as a service to these providers, right? So, in spite of all these biggies in this ecosystem, Netflix is not that big like them, right? It's a company which basically its whole revenue is the money which it gets from the subscribers for the subscription money, which subscription fee, right? But still, it is giving a tough competition and probably is the winner hands down when it comes to streaming. All thanks to the power of this recommendation. People once they get they are onto Netflix, they become so much hooked, they really don't shift. Right? And also at the same point in time, their collection that's also pretty massive. So all these things taken into account is what makes them so special, right? So we have learned these naive base, right? So naive base actually can be used in some kind of a content-based recommender system, content-based recommender system against a particular genre, against a particular movie star, against a particular movie background, theme, the director, the music, all those things, you can actually put it through a naive-based process or system and feed it to the recommender system, which will give you some kind of a recommendation. Also, another way of doing recommendation is via decision tree, which we are going to get introduced shortly. Right? So decision tree is where the different decisions, they are broken into smaller and smaller parts based on certain features, and that also can be used to give you some kind of a recommendation, right? Okay, so yeah, let me pause here for some time. Let me take some questions from you and then move on to the next part, which is that of this decision tree. Yeah, question time, questions, any questions? If you're planning to sit for some kind of interviews, maybe internal to your organization, or again, you are going and trying to probably look for some kind of a job outside, just do one thing. Just find out that, okay, what is the domain of interest of the particular organization that you have been talk- uh, uh, you're trying to apply. See if they are using some kind of a recommender system or not. It's there. Probably try and get some more knowledge on the particular domain. Right? Okay. So then let's move to our topic of this decision tree. Right? The first question: why learn about this whole decision tree? Right? What's the requirement? What's the use? Right? So decision tree, like the all the algorithms which you have learned, it's another algorithm for your machine learning, right? But again, why another algorithm? See, the algorithms which we have discussed already, things like your KNN algorithm, k nearest neighbor algorithm, algorithms like those of regression. Uh, so after doing those sessions, probably you know a lot of those algorithms. You probably can implement those algorithms as well. But when you explain these algorithms to someone who doesn't have any clue on those algorithms, right? What happens is that the discussion doesn't turn very good. So let's say that you are someone who knows a lot about machine learning. You know all the concepts of machine learning, deep learning, everything you already know, and you have built a fantastic model. And then your boss, who doesn't have any clue about all this machine learning and everything, he or she asks you that, okay, fine, can you explain that what exactly have you found out here? And then if you try to explain him or her knife base or KNN or something else, you understand, right? The problem which will happen, and maybe he or she will just shrug you off. That is where decision tree, the power of decision tree, that comes in, right? So in decision tree, what happens is that the entire process of taking the decision, that comes via a beautiful tree kind of a structure. There is a flow diagram, flow like structure, which is there, and it's very well interpreted also. Right? It can be very well interpreted, and that's the beauty, or that's the success of decision tree. Right? If you go and show someone being structured that, okay, this is how the decision has been taken, right? They still might ask you that, okay, how did you get this? Right? So you can say that I got this mathematically, right? There is a process which is there behind this, and that's how I got it. Uh, so if you're not further interrogated, it is fine. If you're still interrogated, yeah, you can still go ahead and discuss that how it happens, right? But that's the whole part. That once you are showing the tree diagram or the flow kind of structure, people generally becomes satisfied. Right? Another part with the decision tree is that it can take into account both categorical as well as continuous variable. Right? You can take both these things into account. Right? And because it can take into account both the categorical and the continuous variable, both at the sides of the features as well as the target. On the feature side also, it can take both categorical as well as continuous variable. On the target part also, it can take up both categorical as well as continuous variables. So that's why you can solve both classification as well as regression problems using decision tree. Right? Also, another part is that this decision tree, they are very robust to all this missing values and outliers. Right? So these are the motivations for learning about a decision tree. Right? Some simple trivial examples I have for you, right? So one of these example is that let's say the age of a particular person, right? So I'm trying to come to some model which will help determine the kind of premium which someone has to pay, right? Now, looking at the age part, if the age is generally more than 50, so irrespective of the medical history of the person, if you are trying to buy insurance, you need to pay a high premium for this insurance, right? You need to pay a high premium. Why? Because again, the age is more than a particular threshold value that you are looking at. Come to the case of where the age is probably less than 50. In that case, uh, uh, one part is obviously the age. With the age, the premium gets high. But along with the other thing will also come into play. What kind of a coverage I am looking into, right? So if I'm looking into a maximum coverage, high coverage, okay, then in that particular case, you need to give this high premium which is there, right? Now, let's say that you are not looking for a maximum coverage, right? So this is maximum coverage. Yes, you are not looking for a maximum coverage. You are fine with some basic coverage. Then probably the question will come is that are there any medical history or reports which are there, right? Are there some issues in the medical tests and everything? Yeah, it is there. Then unfortunately you have to pay high premium. If not, if there are no issues, then the premium will become low. Right? A simple decision. Now again, obviously a question might come is that how we got into this particular decision. Obviously that came from the data, we'll come to that. But again, if you see the structure of how you're getting the whole process of deciphering or making the prediction, it is so simple, easy to understand, intuitive, that you don't require anything else apart from this, right? So that's the beauty or goal of this decision tree, right? So let me just a moment, just a moment. Yeah. Okay. So how does this whole decision tree kind of process happens, right? One thing we need to find out is that which is the best variable for splitting, right? So how do we get this best variable for splitting, right? How did we know that first we had to split based on the age, right? Now this particular part is very simple. It comes from basic statistics also, right? You look into all the features of the data which has been given to you and find out that of all the features given to you, which one of the features are contributing most to the decision process. And that basically becomes your base variable for doing the split, right? And once you take the first variable, now you go and move to the second variable, third variable. Like that, you keep on doing this until you have reached a state where all your decisions are completely made, right? So, just a moment. Let me help you out with some, once again, trivial examples, which will help you understand this whole process better. Open up. By the way, I hope that you have received all the slides, right? There is nothing remaining on my part. So I've shared all the slides in advance, whatever we'll be covering, so that you don't get into the problems which you had last time, right? So just a minute. Yeah. Okay. So, decision tree. Just a minute. Yeah. Here is the example which I was looking at, just to make you understand better. Okay. See this particular example. Right? So here, what exactly we are looking at? So this is the actual tree, right? Actual tree. Right? This is the actual tree. Here is the root comes here. This is the stem. Roots are probably all out here, stem. And these are the different branches, leaves, all these are out here, right? The branches and the leaves. So this is the actual tree. The decision tree, what happens is that it looks the thing at the other way around. So here in the decision tree, here is the root node. This is where everything starts. And from the root node, we start and getting to the branches. So it's almost like the tree, the real tree inverted. That basically becomes my decision tree, right? That becomes my decision tree. Now let's look into this whole process. Right? What exactly has happened? Right? Let me ask you that if you are trying to change a job, right? The first thing I'm sure that most of you you'd be looking at, okay, how much extra money will I get? Right? So the salary part, that is probably the very first consideration that you'll make. Salary at least 50,000, right? That's the first consideration that you are doing, right? So if the salary is not high, right, salary 50,000 again, some point in time in the USA, minimum 50,000 salary, if you're not giving for white collar jobs, people were rejecting them. So yeah, if you're not giving that, then decline the offer. If the salary is at least 50,000, if it's yes, good, right? Then probably the other things people will look into. Right? So people who stays probably in places like Bangalore, you know that how difficult is the commute in Bangalore, right? So if the commute is more than an hour, right? You know the kind of problem which you have. So then decline the offer. Right? Commute is less than an hour, fine, good, right? Then does it offer some kind of a freebies, free coffee, free lunch? Yes. Then accept the offer. Otherwise, decline the offer. Right? This is a simple process in which the decision was happening out here. Right? Some people, again, I'm sure that in the class, there will be some people who will say that, no, professor, for me, this commute part is very important, right? Because maybe I have a small kid at home. I can't spend the entire day commuting all that part. But again, try to understand one thing that is probably very specific to you and a small group of people. Right? If I look into the majority, or the majority of the people, the salary is probably something which is of utmost importance, right? So that's why that comes as the most important variable for doing the split, right? I'm sure that the other variable which you're talking about, that's also important. But whenever we are building some kind of a model, some kind of a process we are building, we have to ensure that this process is more and more generalized, right? The salary part, if we use that as the variable, splitting variable, what happens is that it takes into account a lot of the different cases which it had encountered, right? That's why that's the first important variable which was out here, right? Okay, so these are the advantages of decision tree, right? Easy to understand, useful in data exploration, less data cleaning required, data type is not a constraint, and then finally the non-parametric method, right? Easy to understand, right? We are shortly going to discuss decision tree going ahead, and you will find that how easy it is for you to understand the decision tree, right? Even people from the non-analytical background, even if you don't have too much of a knowledge or too much of idea, right, about analytics, the kind of logic which brings about decision tree is pretty simple, pretty trivial, right? So that is one of the reason. The second part is useful in data exploration. Right? Using decision tree, you can quickly identify the most significant variables and the relationship between many of these variables. Right? You can create new variables, new features, right? And all this you can use for the data exploration to the content. So very good for the data exploration part. The third is less data cleaning required, right? See, one of the biggest challenges of machine learning is that you have to do a lot of data cleaning, right? That's a problem, right? Uh, Fortunately, decision tree, right? Though again, I'm never saying that you don't need to do data cleaning for decision tree. Please don't have this thing in your mind, right? I've actually seen in some responses from previous batches where people have said that in decision tree, you don't require any data cleaning. It's not that you don't require, you require lesser data cleaning, right? There is a difference, right? You require lesser data cleaning in decision tree compared to other models. Many of the other models are heavily reliant on your clean data. If they're not getting exact data, clean data, they are not able to make a model. Fortunately, with decision tree, even if the data is a bit untidy, right? So it can make reasonable approximations and still give you very good trees, right? And data type is not a constraint. As I said, that you can take any kind of a data in both the feature as well as the targeting decision tree. Right? In the feature side also, you can have different kinds of data like categorical variable, like numerical variable, binary variable. Also in the target side also, you can have different kinds of data, right? So both on the feature as well as target, you can have multiple kinds of data. And then finally, it's a non-parametric method. Now, what exactly is a parametric and what exactly is a non-parametric method? The parametric method. What happens in the case of a non-parametric method is that a parametric method is that we will make some kind of a assumption about the underlying model structure. See, for example, you have learned linear regression, right? So linear regression, what happens is that linear regression assumes that the pattern of the data will be some kind of a linear in nature, right? The way the different variables they are interrelated, you will have some kind of a linearity within them. That's uh, the parametric method. Even if for the logistic regression, you assume that there will be some kind of a kind of a curve which is there, which will happen for the case of this logistic regression, right? Decision tree, on the other hand side, it's a non-parametric method. It does not make any kind of assumption, and it's also not required to make any kind of assumptions as far as this decision tree is concerned, right? It will make no assumptions about the underlying structure. Whatever data it encounters, it will probably do the plotting accordingly. Right? So these are some of the terminologies in decision tree. The first thing which is called is the root node. So root node is the place of the part where all the data is present. All parts of the data are present in the root node, the entire population. Right? That's the root node part. Then comes splitting part. What is splitting? So in the root node, you have both the target as well as the features, right? So when you're taking into account all the different values in the root node, as I said, that some feature will come out as more prominent compared to the other for doing the splitting. For example, the case which I had just discussed, the case for that accepting or rejecting a salary offer, right? In that particular case, what you find is that what is the salary which is being offered, that becomes one of the very important features to split a tree, right? Very important features to split the tree, right? So which are the important features which are there? So that particular part is getting determined in the splitting part. Now once you split based on a particular feature, right? Once you split on that particular part where the salary is less than 50 or more than less than 50,000 or more than $50,000. So obviously your data becomes bifurcated, right? On some part of the data, you have the cases where the salary is less than 50,000. On some part of the cases, you have the pieces where the salary is more than 50,000, right? In all these cases, what you do is that then you take this subdivisions and you analyze the other variables in those subdivisions, right? That's what keeps on happening. So you get some kind of a decision node based on the splitting variable decision node. And like this, you keep on splitting until and unless there is nothing else remaining to split. So these are the terminal nodes, also called the leaf nodes, which are out there. Right? So these are some of the terminologies that we are going to encounter. Right? Depth of the tree is basically the length of the longest part from the root node to the leaf node, longest part. So 1 jump, 2 jump, 3 jump. So this decision tree has a this thing as a depth of 3, right? Because again, it requires 3 levels to go from the root to that of the terminal nodes, right? So you might also question that, professor, then why not this one like this and then this? This is true. It clearly said it's the longest part, not the shortest part. So the length of the longest part is what determines the depth of this particular tree, right? Okay, let's move ahead. These are the different decision tree algorithms, right? ID3, C4.5, 5.0, kite, art. We are going to discuss some of them, right? Not all of them, but some of them we are going to discuss in details, and I'll also take you through the underlying mathematics, and you'll find that it's not very difficult. It's not very difficult if you look into it. Right? So these are the steps for generating the decision. First, what you do is that you start with the root node, in which all the data is present. That's your first starting point. And once you have the root node, right, then you decide on the splitting criteria as well as the stopping criteria. Stopping criteria will come data point in time. Splitting criteria. Splitting criteria, I've already said that the variable which is best suited for doing the splitting, right? You find out that particular variable, right? And how you find out that particular variable, that also comes via a process of a mathematical process of induction, right? We're going to discuss that. But you can decide on the splitting criteria, and then what happens is that the root node is split into 2 or more subsets leading to tree branches, 2 or more subsets, right? And these are called as the internal nodes, right? So each of this internal node has only one incoming edge, right? So let me go back to the previous diagram, right? So these are some kinds of internal nodes which are there, right? These are some kind of internal nodes which are there. So as you can see, for each internal node, there is only one incoming, right? But again, the outgoing can be one or more, or even none in the case of the internal nodes, right? Okay. So we keep on this process of splitting until no further splitting is possible. No further splitting is possible, or the stopping criteria is met. Right? So the terminal node, whatever is the terminal node, the last node, that will have no outgoing edges. Right? So that is when we stop going of this particular. Right? And these terminal nodes are the ones which are used for generating all the business rules. Right? So this is a simple flowchart for a decision tree. So either you would like to do some kind of a classification, or you would like to do some kind of a prediction. So prediction means some kind of a numerical target, and classification means some kind of a categorical target. Right? So again, typically what happens is that if you are, so again, depending on your target variable, you have to find out that whether you're trying to do some kind of a classification or doing some kind of prediction. If it's classification, then you have to do a classification tree. If it's some kind of a this thing, continuous value, you have to do some kind of a regression. Right? If the response variable has only two categories are there, use a standard classification tree, a binary classification tree. Multiple categories, use something called as a C4.5 implication, which we are going to do in the class today. Right? And the other part is that if the response variable is continuous, right? Then if the relationship is little linear between the predictor and the response, use standard regression tree, which is basically a parametric method. Or if it's a non-linear relationship, then use the C4.5 implementation, right? It has multiple categories or targets, C4.5. Right? Okay. So finding a problem fit for classification. A very simple thing is this one. Target value as discrete output values such as yes or no. That is your indication that it is going to be a classification, right? So an example of classification tree. After this, we are going to take a break, right? A very simple one. That whether a person is fit or not, that's the business problem that you're going to solve. And for the business problem, you have been given data regarding fit and unfit people. And then you have also been given information about their eating habit, their exercise habit, as well as their age. The first thing to look into is that from the data it was found out, the first thing to look into is the age of the person. The age of the person is more than 30, right? People, senior people like me, right? If the age is more, then irrespective of my eating habits, whatever it is there, I need to do some kind of exercise to keep myself fit. Otherwise, any kind of problems will come. So if the person is exercising in the morning, yes, it is fit. No, unfit. Take the case where the age is less than 50, young person. In that particular case, if the person is eating a lot of junk or not, right? If the person is eating a lot of junk, then this particular person is unfit. Otherwise, this particular person is fit, right? Very simple if else then kind of a rules which are required for you to come to the decisions, right? Simple and very intuitive, right? But again, how you're getting these variables, like the age will be the variable which is required, or the exercise, that's the first variable, or the it's junk food pizza, that's the first variable. How do you get those things? So yeah, that is where a lot of the underlying algorithm, some kind of a mathematics will come into the whole picture, right? So let's do one thing. Let's take a break, right? And come back post this break. So again, it's exactly 11:46 in my clock, right? Let's come back sharp at 12 o'clock and continue with the discussion, right? Should we go and take this break? Yes, no, maybe. Okay. It's exactly halfway through the class. So yeah, let's take this particular break. I'm stopping the sharing, right? And yeah, let's come back exactly, as I said, at 12 o'clock and restart the session. Thank you, everyone. Okay, let's slowly come back. I hope this break was useful for you. Okay. Yeah, slides are visible. Kindly confirm slides are visible. Okay. So decision-tree criteria. On what basis, on what criteria do you work on this decision? Right. So here, basically, these are the three important things that we'll look into. One is called a splitting criteria. One is called a merging criteria. The other is called a stopping criteria. Merging criteria at this point in time, let's not focus on it. We'll focus more on the splitting as well as the stopping criteria. Right? Okay. So steps for generating the decision tree. It starts first with a root node on which the data is present, and then it decides on the splitting as well as the stopping criteria. Right? As I said, that those two are very important. And then what happens is the root node is split into one or two more subsets leading to something called as tree or branches. Let's see how that happens. Right? So let me show you this particular example. Right? So here you see this data. Right? This data is that of people who are going out to play tennis, right? And the different features which are there are outlook of the temperature, right? Humidity, wind, and finally this play decision is your target variable. Right? This is your target variable. Now, basis this, how can we find this out? Right? See, if this is your target variable is having these two things, play yes and play no. Right? So we have to build a model which will give us, which will help us determine that whether this particular person will go out and play things or not. Right? A quick count from your side is that how many of the data point are saying that yeah, you can go out and play tennis, and how many of the data point are saying that you can't go out and play tennis. Right? Yeah. How many? How many? So Shukantu is saying 9 years. Okay, fine. And what about the other cases? 9 years cases are there. True. What are no cases? 6 no. Is it 6 no? I think it is 5 no. 14 cases are there. So 9 yeses and 5 no cases are there. Right? So let's say that you have not built any model. You have not built any model. Then what will happen is that your default prediction would be that of the yes default prediction. Because again, if I look into the records, more number of cases are there for the yes. So that's why we can just go and say that yeah, go out and play tennis. Right? So that is happening. That is happening when we are going via this majority part, right? But again, that is as good as a baseline model, right? I have not applied anything. I've just looked at the majority. But whenever the modeling comes in, that is when the different features, they play a very big role out there. So this is what I would like to do. Want to predict where to play golf based on temperature, humidity, wind outlook, all these things. So these are the questions: which feature to take first, why to take a feature first, and what determines which feature to select. These are some of the questions that I need to answer, right? Okay. So this is the quick statistics which I was talking about. Total 14 cases, 9 cases for should not be play tennis, we play golf, and 5 cases for don't play golf. Right? This is the quick statistics which I have. Then how can I create the decision tree? The first part is that I'll basically create some kind of a segregation from the data. So let's say that I split based on the temperature. Right? I split based on the temperature, and let's say if temperature is greater than equal to mild, then play golf, else don't play golf. Right? Now here, if I have very clear indication, very clear division that okay, if I split based on the temperature, always it will give me these two parts, play and don't play. Right? Very clearly it will come out from this. If that happens, then my problem is solved. I've got my exact feature. This is which I can say whether to select this particular person or not. So let's say that here is a company which would look into people with let's say a engineering degree in computer science and 5 years or more of experience. So if I can just use that particular, or let's say 5 years or more of experience with that particular part, if I can just look into the background of the person, right? So background engineering, then select yes, otherwise select no. So my one variable is quickly helping me get to the decision, right? Now we have to find out which that particular variable is. So sometimes what might so also happen is that after I have done splitting based on one variable, let's say here this was the temperature variable. After this was used, this particular part was fine, right? But the other part was still not fine. This particular part, still a lot of ambiguity is there. Then you use the second variable. Right? And then after doing the second variable, then probably let's say the ambiguity has got resolved. The previous example which I told you, right? So let's say this company was there which was taking engineers. So people who are non-engineers, they will say that okay, we don't want to apply because we know will not get selected. And people who are engineers, they say, yeah, we'll apply because again we know definitely will get selected. Right? Now after the application process happens, so this is the part of, let's say, non-engineer. So non-engineer, they are not going out and playing, right? Not getting selected. For the case of engineer, first it was found out, they thought that okay, engineers means everyone will be taken, but it was not the case. Then it was found out that okay, not only the engineering part, right? This is the engineering feature. Not only the engineering part, the work X is probably also important. So work X greater than 5 years, yes, I'll select. Less than 5 years, no, I'll not select. If I include that particular feature, then probably my problem gets solved. Right? So like this, we'll have to do. Right? We'll have to find out iteratively which features are important, and this is that we are going to solve this problem. Right? So how to do it? It comes from an old principle, old saying, which is called divide and conquer. Right? Divide and conquer. So how can we do the divide and conquer? Right? So we select some kind of a test for this root node. Right? What kind of test? We are just going to discuss and create a branch for each of the possible outcome of the test. So let's say you are having 5 variables. For the case of that interview, which we're talking about, let's say you had so many variables. You had variables like, let's say, the background education of the person, engineer, non-engineer. You had the gender of the person, right? Male, female. You had the age of the person, right? And at the same point in time, you also had the years of experience of the person. Now, what you do is that you iteratively you split the data based on each of these features. Wherever you are finding that the split is helping you take the decision to the maximum possible extent, that is becoming your final feature for the splitting the feature, right? So the first thing which algorithm which I'm going to talk about is something called as KIDE. Right? So KIDE is basically for chi-square interaction detection algorithm. Right? So it does the decision tree, creates the decision tree based on this chi-square test. By the way, how many of you knows about chi-square test, have studied chi-square test? Was it there as part of your statistics? Chi-square test. Chi-square test of homogeneity, was it there as part of your statistics? Sukant is saying yes, it was there. Okay, fine. So here, what we are going to do is we are going to use the chi-square principle out there, right, in business stats. So I'll again just show you how we are going to do that. So this is the formula for this chi-square test, right? Where OI is the observed value and EI is the expected value. So observed minus expected whole square by expected, right? C is the degrees of freedom. Again, I'm not going to come to the degrees of freedom. Let's look into the observed and the expected value, right? So how we can use this, right? So let's look into the humidity value, right? In total, if you remember, I had total 14 records, of which 7 were belonging to humidity high and 6 were belonging to humidity low, right? Also, the other thing which is there is that of the 7 cases of humidity high, there were 3 which were saying that yes, go out and play tennis, play golf, and 4 which were saying that okay, don't go and play golf. For the cases humidity low, 6 cases were there which were going and saying yes, go and play, and 1 case was saying that no, don't go and play. Now, even before we go to any formula, any mathematics, just look into this data once again. So if my humidity is low, a large chunk of the decision is asking me to go out and play. So only 1 of the 7 is saying that don't go. 6 are saying go. Whereas in this particular case, where the humidity is high, it's almost equally split between 3 and 4. Right? 3, 4, very difficult, right? For example, for the low case, it is pretty obvious. For the high case, it is not there. Now, how can I then use this for my decision? Right? So here the basis in this chi-square test, the chi test, is that I'm assuming that this particular feature, they are not having any kind of a influence in the decision. I repeat, not having any influence on the decision, not having any influence. If they're not having any kind of influence on the decision, then what will happen? If they're not having any decision on the influence, then even if I use this particular feature, right, I'll be equally split between the yes and the no cases, right? Okay, let me give you a fun trivial example. So let's say that there are people who studies hard before their exams, the TE exams, and there are people who probably relies on some kind of jari booty, some Babaji booty kind of thing for this passing the exams, right? Now, so your result when I analyze, so there are people who have put a lot of hard work, and then there are people who have, let's say, taken this Babaji ki boti or something like that. And when the results came out, when we were analyzing, we found that okay, people who have worked hard, for them, scores were really very good. People who have not worked hard, scores were bad. Come to the case where people who had taken this this davai, this Jadu Mantar, right? So for them, it was found out that okay, people who had taken this pill, they didn't have much effect on this thing, on the outcome. So I have people who passed also, who took the skills, and people who did not pass also who took the skills. So which means that taking a decision based on this skills part is something which is not adding any much value to my whole part, right? So that is where the expected part comes in. So I have 7 cases, right? So forget the actually how many are yes and how many are no. If 7 cases are there, and if this particular variable is not having any kind of impact, so then it should be equally split between the yes and the no cases, right? So those 3.5, I know it's a fractional number. It's not possible. It should be whole number, but yeah, mathematically that's what we do, right? We split it equally. So 3.5 should go for yes, 3.5 should go for no. Come to the case of low. Once again, here 7 cases I have. So 3.5 should go for yes and 3.5 should go for no. Now, after I did this, then I'm applying this chi-square formula. Observed minus expected whole square by expected. Observed minus expected whole square by expected. So observed is the actual value. Expected is this one. So observed minus expected by whole square by expected, right? This one is also observed minus expected whole square by expected. So this is the values coming chi-square yes and chi-square no. Small values. Sorry, my bad. Take the case of this low value. Here, just excuse me, I'll just take some water. Here, if you see the observed versus the expected, right? The observed is a high value for yes and the low value for this no. Whereas expected was equal between the two. So once I calculate this chi-square value, you find that I have got a higher chi-square value, right? This is the one which I've got. So from here itself, going by the simple logic which I said in the very beginning, that I see that for all the cases which I'm having out here, right? For all the 7 cases which I'm having out here for the low, a large part of it is pointing towards the yes and a small part of it is pointing towards the no. Which means that if I split my data based on this low part, right, maybe because the majority is saying yes, I'll go for this yes. For the case of this high part, this, so you can take the numbers and you can say no was the majority, but again, I mean 3 and 4, you understand, right? It is very close together. Whereas for the low, the ambiguity is much lesser. And that's why here you find a higher value of chi-square, right? A higher value of chi-square is what we find out here. Let's do the same thing for the others as well, right? Look in the case of that of the wind, right? Look in the case of that of the wind. So for the wind, right, once again, in total, you have this 14 cases you're having, right? You're having this 14 cases. Of this 14, 9 are yes and 5 are no. We already knew that, right? 9 yes cases are there, 5 no cases are there. Now, how this yes and no are interacting with the wind variable? For the case of wind is strong. For the case of this, sorry, wind as strong. Here I'm seeing that there are 3 yes cases and 3 no cases. So wind strong, 3 yes, 3 no. I'm equally split between the two parts, 3 yes and 3 no. Okay. Which means that if the wind is strong, I can't take any decision, right? Equal number of cases. Whereas look in the case of this wind as weak, 6 yes and 2 no. Here I'm on a much stronger footing, saying that okay, there is a majority chance that they will go out and play. Right? Got the idea? So then let's apply our principle and apply the chi-square formula. Right? So from our principle, what we find is that here 8 cases are there, 2 classes are there. So these 8 cases should be equally split in the 2 classes. So my expected value for each of the classes is 4. So 6 minus 4 whole square, right, which is 6 minus 4 is 2 square, which is 4, divided by the expected, right, which is this one. So observe minus expected whole square by expected, right? and the other is this 2 minus 8 whole square. 2 minus 4 whole square, right? So 2 minus 4 is once again minus 2 square is 4. So 4 by expected 4, right? So 4 by 4 is 1. So this is for the chi-square, yes. This is for the chi-square, no. And for the strong, the observed and the expected is the same, right? If this particular variable is not having any implication, so it will be equally split between these two. So that's why the value I'm getting 0 and 0. So this is my overall chi-square for the wind feature. So like this, what I'm going to do is I'm going to do the same kind of a calculation for the other variables as well. Outlook. Play tennis. This is my outlook feature. For the outlook feature, I have 14 cases, right? Once again, your 9 yes and 5 no. And as I said, there are 5 cases out here, so 2.5 is expected. 4 cases out here, 2 is the expected. 5 cases out here, 2.5 is expected because 2 classes are there. These are all the chi-square values which we have calculated. So this is the chi-square for the outlook, right? So like this, I also find out that for the temperature. And once it is being done, these are the different values for the chi-square which I got for each of these variables: outlook, temperature, wind, and humidity. You should remember, when my observed and the expected value, they are the same, which means this particular value is equally split between the two or again the multiple output classes. Then what is happening is that I'm unable to take some kind of a decision. Right? So in those cases, the chi-square value is low, while in the cases where the observed and the expected, they are different, right? The chi-square value is high. So here, of all the chi-square value I have calculated, I find the outlook has the maximum chi-square value. So what I'm going to do is I'm going to split my decision tree based on this outlook first. Now you see what has happened when I have split based on the outlook. When I have split based on the outlook, what has happened is that for the case of this overcast, all the decisions, they are homogeneous. All are saying yes, 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 which means that if my outlook is overcast, I don't have any ambiguity in taking the decision. There's no ambiguity in taking the decision. Let's come to the case of the sunny. For the sunny case, though, what is happening is 1, 2, 3 no cases and 2 yes cases. 3 no and 2 yes. Right? So which means that if I don't split further for the outlook sunny part, because my majority is no, so I'll probably have to go as no for this. On the other side, for the outlook rain, here my majority is yes, right? Decision yes, yes, 3 yes and 2 no. Majority is yes. So that's why my final output will also become yes in this particular case. Right? Now for the case of overcast, I'm done. Right? My decision is already taken. Outlook overcast, decision is yes. Come to the case of outlook sunny. So here I have 5 values, 3 are saying no and 2 are saying yes. Once again, what I'm going to do is that I'm going to split based on this outlook variable. Right? I'm going to split based on this outlook variable, and this time, right? See, I can't split. Sorry, my bad. I'm not going to split based on the outlook variable. I'm going to split the data in the outlook variable. Here, if you see outlook, so here outlook is constant, sunny, right? So obviously I can't split based on the outlook. So I have to split based on the temperature, humidity, and the wind part. These 3 variables. So what we'll do is once again we'll follow the same process. For temperature, right? For humidity, 5 cases are there. 2 yes, 3 no, right? Once again I find out the chi-square values. For wind, there were these 5 cases and 2 yes and 3 no. Once again, I find out this chi-square values, and temperature, once again I do that. So these are the values which I've got when I have splitted the data in that particular arm, right, where the only the outlook sunny was there. My question to the class, what do you think? Now, on which variable should we do the splitting? On which variable should we do the splitting? What is your take on this? What is your take on this? Now, on which variable should I do the splitting? Okay, some answers have come in. Ankur is saying humidity. Shukanto is saying temperature. Okay. Some other answers. Let some other people also answer. Some other people. I'll go with Ankur's answer, which is humidity, because you see out here, the humidity is the one which is having a maximum value of chi-square. Humidity is having a maximum value of chi-square. So that's the variable on which we are going to do the splitting, not the temperature, not the temperature. So see, now I have for the sunny part, I have split based on the humidity. So humidity high, 3 cases. So humidity high, 3 cases, all are saying no, and humidity normal, 2 cases, all are saying yes. Right? So see, I don't have any further ambiguity out here. So if the outlook is sunny and the humidity is high, the decision is don't go and play. If the outlook is sunny and the humidity is normal, the decision is yes, go out and play. If the outlook is overcast, the decision is yes, go out and play. If the outlook is rain, now I have some problem, because there are 5 cases and 3 are saying yes and 2 are saying no. So maybe what I need to do is I probably need to just go with the majority, and that will be yes, right? So still there's some problem, right? Because again, if I'm going with the majority, what is happening is after the training has completed, for these cases of these 2 cases of this no, right? Because I'm going with the majority, these 2 cases of no, I'll misclassify them as yes, isn't it? So because of this misclassification, they will give me incorrect results. So probably I can do one thing, that I can keep splitting until the homogeneity has been reached. And now once again, for the other part, this is the chi-square values. I'm not showing the calculation. And now if I, so you can see wind has the maximum chi-square. If I split based on the wind, then you're finding that wind weak, decision is completely yes, and wind strong, decision is completely no. My decision tree has been created. Right? Okay. My question to the class is that now that you have seen this, what do you think are the problems or issues in this mechanism which we just discussed? Problems or issues? What do you think are the problems out here? Yeah, problems. What do you think are the problems out here? So Ankur is saying we'll keep splitting until we reach a pure node. That's fine. Yeah, that's the objective. That's the objective, Ankur. But what is the issue then? We'll do that. That's exactly the process. That's exactly the process. We'll keep on splitting But again, then what is the issue? One is it might make the tree very long. Sure, it might make the tree very long. Point well taken. Shukanta is saying some variables overlapping in leaves. I did not get the point. I did not get the point. It's not about the variables overlapping. See, I mean, whenever we are taking a decision, right, it's not based on the particular features, right? It's based on the target value. So my decision should make my target value consistent, irrespective of the kind of features which are there. Right? Irrespective of the kind of features which are there, my target should be consistent. Right? Okay. Any other issues which you can think of? Any other issues which you can think of? Any other issues which we can think of? Right? So again, coming via what Ankur had mentioned, right? On the same lines, I'll say the case where your tree becomes too long, you can see that at the end of the day, what might happen is that you might have one or two records only at the child node. One or two records only at the child node. Isn't it? If you're having only one or two records at the child node, what exactly is happening is that there, see, finally I have to create a model. I have to create a simple model which goes via like if else kind of a format, right? If we are having one or two record only at the child node, the problem is that it leads us to something which is called as overfitting of the tree. Overfitting. Now, what does overfitting means? Is that I'm too much dependent on each and every feature to make the prediction. So then see how the prediction it becomes out here, right? So out here the prediction, see though, so here the prediction is if the outlook is rain and if the wind is weak, then the decision yes, else if the wind is strong, then the decision is no. Else if the outlook is overcast, decision is yes. This one was pretty good in the sense it's not very long. Or if the humidity is high, outlook is sunny and the humidity is high, then play no, don't play. Or if the humidity is normal, yes, go out and play. Right? And like this, right? So here I had only few features. If we had more and more features, what will happen is that the tree will become longer and longer, and the same point in time it will become overcomplicated till a point that we are unable to take a decision from it. Because again, probably each and every value of the decision tree it will take, right? Outlook overcast, temperature hot, humidity high, wind weak, then decision is yes. Right? Now whenever we are talking of creating a model can't be like that, right? So it almost becomes like for each and every decision, I have to go through all the features and give out that kind of a value which I got in the training record. So it's almost like before the exam, right? You are just memorizing everything which has been told to you without really understanding. You have just memorized, and if something comes from that, well and good, right? You are in for luck, and you are able to give a good answer. If something outside this particular part comes in, then though you are in for bad luck. And in that particular case, what has happened is that you are unable to take a decision in that particular part. Right? So that is basically the overfitting which we were going to discuss. Right? Now this overfitting is obviously a big problem, as you can understand. Right? Because it is not allowing me to create a model. What it is doing is that I am just memorizing the values which are there. So that is where the process of pruning a tree, right? Stopping criterion, those kind of things will come into place, right? So let's discuss that. But until now, understood what exactly are the problems? Understood, right? This whole process of chi-square, right? Observe minus expected whole square by expected, right? I hope you got the idea. In any case, see, these days, what happens is that you won't have to do this calculation in your hand, right? So though maybe in the some of the quizzes, I might give you just some small questions on this, but most of these things are being done by the system only. But again, the system, it is doing the calculation. But again, if you don't understand that how the calculation is being done, then as an analyst, that probably is a failure from your side. You should be able to look into the value, as well as you should be able to analyze these values as well, right? So that's what we are going to do now, that we are going to look into this overfit and the underfit part of the decision tree right now. Okay? So let's move ahead. So building a decision tree, select a feature and split the data to get into a binary kind of tree. Right? That is what we are going to do. And then ask more and more questions until and unless, how long to keep splitting? Until one, the leaf nodes are completely pure, as we said. So the nodes will be completely pure. We don't have any kind of ambiguity in terms of the leaf nodes or the final nodes, right? Or some kind of a depth is reached. So as Ankur was saying that the tree has become too deep. So let's probably have a tree which is shallow. So let's say that, okay, I don't want a very deep tree. If the depth is up to level 2, it should be fine with me. So let's create a decision tree of a depth up to maximum depth up to 2 only. That's another way of looking at it. Maximum depth is reached, or some kind of a performance metric is achieved. Some kind of a performance metric is achieved. Performance metric in the sense that, see, whenever you are splitting the tree and building this complete tree, what happens is that because this tree is completely homogeneous, so if you're trying to check the efficiency of this particular tree, the accuracy of this particular tree, then what happens is that the efficiency or the accuracy becomes 100%. But again, this 100% is there on the training data, right? Now, let's say that you are saying that, okay, I'm fine with as long as you are giving me an efficiency or an accuracy of, let's say, 80%. I don't want to go beyond that, right? So then in that particular case, when I have started splitting the tree, then if I'm able to come up to a point where it is giving me 80%, at least 80% kind of accuracy, then I'm fine. I don't need to split further, right? So how 80% accuracy? Let me show you the example. Right? So see in this particular tree, if I look into the overcast part, all the decisions are yes, yes, yes. So my actual and the expected decision that will also become yes from this particular part. So 100% accuracy. See the part where I have split it based on this humidity. So humidity, 5 records are there, 3 humidity high and 2 humidity normal, right? So here also 100%, here is also 100%. Come to the part where the outlook rain is there, right? So outlook raining is there. Here I have 5 records, 3 saying yes and 2 saying no. 5 records, 3 saying yes and 2 saying no. Now, if I'm doing a decision based on this, then what will happen is that of these 5 records, because I'll go with the majority, I'll say all of as yes. So all the 5 I'll say yes. But again, actually 5 should not be yes. There will be 5 yes, 3 yes and 2 no. So this 2 no, I would have misclassified, and that's the problem. That's the problem, right? So of these 5 records, 2 I would have misclassified, but 3 I would have classified, right? So on this particular 5 records, since I am doing 3 correct classifications only, so 3 by 5, which is 60% accuracy is out here. Here, of the 5 records, 5 are correctly classified. So 5 of 5, 100% accuracy is there. So here, once again, 3 of 3 correctly classified, 100%. Here, 2 of 2 are correctly classified, so 100%. So what I need to do is I need to take a weighted average of all these values. Right? Or otherwise, if you can see these values, I had 14 records. 1, 2, 3, 4, 4 from here, 3 from here, 4 plus 3 is 7, plus 2 is 9, 9 plus 5 is 14. Of these 14 records, I have done 2 misclassifications, right? This 2 I probably would have misclassified. So which means 12 of these 14, they have been correctly classified. 12 of the 14 are correctly classified. So my accuracy here is, so 12 by 14 is how much? 12 by 14, let me do a calculation. 12 by 14, that is 85.71. If my threshold performance was 80%, so then with this particular configuration, I have already done a 85% accuracy. So I've already gone over the maximum threshold which was given to me. Right? So then I can stop there. I don't need to split it further based on this particular part range, because again, whatever was the performance threshold which was given to me, right, I have already achieved that. Right? So again, this I spoke in terms of the accuracy part. If I use some other metric, let's say the precision or the recall whatsoever, so then probably I would have to check that how much it is coming basis on those particular metrics. So this is how long I should keep splitting the tree, right? Okay. So this becomes my final decision tree, right? And this particular final decision tree, as you can see, that it becomes a complicated one, right? If you split it further, you can further fit. Okay, Ankur is having a very interesting question. Performance metric is on the train data or on the test data? So Ankur, so generally when we talk about the performance metric, so you can check the performance metric both on the train data as well as on the test data. But in reality, when we are looking into the applicability of the model, right? How much fit the model is, how much generalized the model is, we generally look into the performance metric on the test data or the validation data. But again, that does not mean that you can't run the performance metric on the training data. You can obviously run the performance metric on the training data as well. Right? And in the case of a decision tree, if you make the decision tree completely homogeneous, then on the training data, always you will get a 100% kind of a performance guarantee. Right? That will happen in the decision. Right? Okay. So Ankur is asking the 80% was on the test data, right? So here, see Ankur, I mean, here I'm just giving you the idea. So 80% we have done on the training data only, not on the test data. Because on this data only, I'm getting my model trained. So on the training data only, we have found it out. But again, in reality, as you said, that this 80% thing will do on the test data and not on the validation data and not on the training data. Right? Okay, let's move ahead. So, as I said, that select a feature, split the decision binary, continue splitting, right? So, these are the ones. Leaf node pure, only 1 plus image, maximum depth range, and performance metric is observed. Right? Okay. We've already discussed one of the methods which can be used for splitting the tree, right? Let me take you through some of the other methods also, right? So one thing you can understand is that this decision tree is a very greedy method. Greedy method in the sense that it evaluates all the values, each and every value it evaluates before finally it comes to the particular part, right? Before it finally comes to this particular part of the decision, right? So one thing which we used was this chi-square part, right? We are going to learn something new, which is called as an attribute selection measure. So by the way, this chi-square also what we did, it was the attribute selection measure, which was used for splitting. We'll use some other attribute selection measures as well, right? So we are going to talk something about this thing called this classification error, Gini index, and entropy. Now let's see what are these. I'll just talk about one of this only. There are only few people in the class. I'll just talk about only the classification error part, right? Classification error. So how you find out the classification error? Simple. 1 minus maximum of the proportion of the classes. So here I have 12 records, right? 8 yes and 4 no. So if I look at the proportion of the decision, so 8 are yes, 8 of 12 is yes, and 4 of 12 is no. I repeat, 8 of the 12 is yes, and 4 of the 12 is no. So the classification error is 1 minus maximum of 8 by 12, 4 by 12, which means 1 minus 8 by 12, which is equal to 4 by 12. That is basically my classification error, right, for this particular part. Come here. So here I have 4 records, right, of which 2 are saying yes, 2 are saying no. If I find out the classification errors, it is 1 minus maximum of 2 by 4, comma 2 by 4, which is the same. So it is 1 minus 2 by 4 is half. This is equal to half. That is the classification error which comes out as here. And for this particular part, right, 8 records are there, 6 yes, 2 no are there, right? So 1 minus maximum of 6 by 8 and 2 by 8, which is 1 minus 6 by 8, which is 1 minus 3 by 4, which is equal to 1 by 4. So that becomes my classification error, right? Now, how we are going to use all this classification error, I'll probably not extend to that particular part today, right? I think most of you are having the exam today, right? So what I'll do is I'll probably stop here at this point in time, and let me open this class for questions. Questions, whatever questions you're having, let me ask those, and then probably call it a day. So I've given the permission to allow to all the 3 people who are there in the class. So yeah, questions from your side. Questions. Any questions that you have? So this particular part was more of a mathematical, right? Again, some bit of mathematics will probably require.
So I had one question.
Please.
Regarding the initial part of the decision trees, when you explained that these models are usually very robust to outliers. So I understand that these are non-parametric models. So, but is there any specific reason for that? I would just like to know. I may have missed if you explained. So if you could please explain.
No. So yeah, I didn't get your question. So the non-parametric part you understood. So what is your question? With this,
like any particular part? Sorry,
it is with regard to the outlier part.
Yes.
So here is an example. You see the temperature is greater than equal to mild is the basis on which it is this thing. So again, if I take the temperature as let's say this mild temperature is, let's say 30, right? So this one is less than 30, and this one is less than more than 30. Now 30, 32, 35, let's say 55, or let's say even extreme 62. See, this kind of a temperature is also there, right? See, this particular value or this particular value, these are some kind of outliers.
Yeah.
Right? In terms of my model, the way in which the modeling decision happens. So this outlier is not impacting the decision to that particular extent. Because again, at the end of the day, what I'm doing is I'm doing a divide and split, right? So as like if I have got my point correctly, from where I'll make the divisions properly, right? So this particular outlier value, they are not that much impacting the model in that sense.
So, sir, this would apply for decision trees for regression also, because there, I believe, averages are coming into the picture. So there as well, the outliers won't matter.
But again, see, it depends on what aspect you are talking about the outliers. See, here I am talking the outliers with respect to the feature part.
Yes.
And your question is the outlier with respect to the target part, right? So target part outlier again. So target outlier.
Actually, sorry, I didn't explain. My question was based on features only.
So
Outliers on features.
Give me an example.
So the same example, if the temperatures we were taking and the it was not a classification problem. If it was a regression problem,
okay,
and supposing we have to predict something like wind speed, I'm just making a guess. It might not be technical.
Sure. Why not? Fine.
Yeah, but if our target was supposed to be a continuous number, a variable, so there, if we were using decision trees for regression, there also outliers in the features. They won't matter.
Hey, it will matter in the sense. So what will happen is that at the end of the day, we saw that again we will touch upon the decision tree regression in the next class, not first class. But again, in the decision tree regression, what will happen is that there also what we need to do is we need to look into some kind of a homogeneity value, right? So here, what will happen is the problem which will happen out here is that when you feed in that high value, so let's say here the temperature is, let's say, 55. When you put in this particular value, so maybe the wind speed, what you'll get, so that wind speed part, it will become give me some kind of a erroneous value, right? So in that way, yeah, it will still get affected. But the point is that the extent at which it gets affected, it's not that high like that of the other models. That's the whole point.
Okay.
Right. But again, when we do the decision tree regression in the next class, I think this particular part also will get much more clarified.
Okay.
Okay. Yeah. Any other questions? Anyone? Questions?
Hello.
Yeah.
Sir, this is Ankur. If you could please put the presentations for the next lectures, second, third, and fourth as well. So then we could refer those as well.
I see. What I do is I share everything at the very beginning with the team. Now, how it gets distributed, I don't have any control over that particular part.
Okay.
I don't have any control over the particular part. But again, I think the distribution happens from the point of view of the upgrade, and I coordinate with NM for this this particular part. So to NM, whatever I have to give as per the part of the protocol, we give it at the very beginning.
Okay, thank you, sir.
That you have to check. But again, sometimes what I do in the class is that again, not only with you, but with some other batches also, that if some question comes in, some specific question comes in, which probably are not covered as part of the slides which I'm having. So sometimes I refer to some other slides which I have. This is something which I do day in and day out, right? So I probably refer to those other slides. And sometimes people think that, okay, I've probably not given the correct slide. So whatever is there as part of the syllabus, that is already being shared with them much well in advance.
Okay.
Right? Okay. Yeah. Any other question?
No, sir. Thank you.
No? So I think then let's call it a day then, right? I think people are having their exams also today. So again, I wish you all the best for the exams. Next class, just inform the team members that we'll probably just continue whatever we have done today. But again, for them, what will happen is that they have missed a part of the mathematics part. So for some of them, it might become a little bit difficult in the next class. But again, we'll try to see what can be done about that. So next class, I think we are going to complete decision tree part and stepping into the part of this model selection. That is what we'll do in the next class. And at the end, at the last part, we will do all the hands-on pertaining to this particular part, right? So in the last term, what we did was for the ML1, we had the hands-on in between, but that took away a lot of time from the class.
Sir, sorry, one more question, if you don't mind.
Yeah, why not?
Sir, in the schedule that you have given, the first IA is showing on Thursday, but in the term calendar that we got from Upgrad and NMIMS, the first IA was supposed to be on Saturday of that week. So, sir, has the schedule changed or like?
No, I don't think the schedule has changed. So it's based on the template. The template had probably some standard values, and sometimes because of this festival and everything, that has got this. So forget the Thursday, Friday part. Whatever is the coverage part, right? You can probably focus on the coverage aspect.
Okay, so the first IA would be Saturday only.
First time probably on a Saturday. Right?
Okay, thank you, sir.
I think then let's call it a day. And again, as I said, that next week, let's come back, continue with this particular part. So this particular part of machine learning, in the previous time when we did machine learning, we did not do too much of in mathematics. So here a small bit of mathematics also comes in. See, at the end of the day, this entire domain of machine learning, you need to have 3 specific skills. One skill is definitely the business skill, the understanding of the business and how you can formulate a business problem to a data problem. That's the first skill that you should be having. The second skill that you should be having is some kind of a skill to do the programming, because you need to convert the data set, whatever it is there, into computer codes, which can help you get these decisions and everything. And the third thing is for the modeling part, right? You also need to have some control over the modeling part, some bit of mathematics you need to understand, so that again, at the end of the day, when you are explaining this to someone, right, rather than saying that, okay, this is coming from a black box, which is a decision tree, if you could also explain that, okay, this happens via this divide and conquer process, right? See, no one will probably go deep into the mathematics part, but again, for people who probably aspires to have a long journey in this particular field, looking into interviews and parts, so for them it might be useful. So we will try to cover all the 3 facets. Some of the facets may not be very relevant to some of the other people, but again, it happens from batch to batch. In some batch, I did get this thing. I did get the feedback that here it is all theory and it is implementation Python, too much coding and theory. We do not understand the this thing, the working of the algorithms. And when sometimes the working of the algorithm, we get deep into it, people will say that, okay, the business part, it's not been covered to that extent. So that's why we have a balance of all these 3 parts, right? Whatever suits you as per your own requirement, yeah, you can choose this particular part, right? That is what you do. That. Fine. So yeah, that's all from my end today. I wish you a very happy weekend, and yeah, best of luck for the exam. We're going to meet again in the next class. Thank you all.
Thank you, sir.